Perfect. Thanks, Kai, for organizing this great event on this rainy, sunny afternoon in Brooklyn. So where I come from Austria, we don't usually have CK dives on Sunday. So it's really nice to see this and what can happen in a place like New York, where it's just any random Sunday and you can have a really deep dive on CK. Now we're gonna switch a bit gears, and unfortunately we have to slow down a bit because CK TLS is maybe one of the coolest CK use cases, CK MPC use cases, and as you've seen with the talk, it's more already about how can we defend this technology. Everybody's excited that it will work, so it's not really anymore in the proof of concept phase and has real impact. And today I want to talk about coSNARKs. So they're not as established for now, but that's what I'm excited currently. And my name is Lukas, I'm working at TACEO, and what we primarily do is now doing research and development in the areas of coSNARKs. And I guess not all of you have heard of the term coSNARKs or the more long-form collaborative SNARKs. So how many of you have even heard sometimes? Okay, very few, but I guess all of you have heard the term SNARKs? Yeah, then it's a very easy way to get it to coSNARKs. On a technical side, it's like if coSNARKs are when you combine the best of CK and MPC in a Web3 setting. So if you want to have the good properties of CK and MPC, combine it and think about Web3, that's at least what I think coSNARKs are. The term goes back to a paper in 2022 by Alex and Dan Bonnet, so it's rather recent, even for CK terms. In a more playful way, if you know SNARKs, so why do we even need coSNARKs? Is it just one new proof system? Is it an optimization, or what does it give you? And it extends the capabilities and opportunity that the SNARKs give you. So I want to think of it like, as a kid I did play a lot of soccer. And you got your new ball, for example, and you're very excited, you drag it around, you kick it and so ever, and it's very exciting, but also kind of limited. And I think that's where SNARKs and CK is at the moment. It's this extremely exciting technology we all know that will transform a lot of the digital space we know as today, but it has some certain limitations. So think of like, CK is great for, and I'm talking specifically about the CK use cases for privacy, not about verifiability. So you have CK identity, you have something like the CK TLS, and you have private money transactions, for example, from the smart contract networks, so the CK-based smart contract networks. But once you want to move beyond this sphere, it's kind of limited, and that's exactly if you have a ball or soccer ball, you want to play with your friends, you want to bring them in and make it multi-party. And that's what coSNARKs are allowing you. It allows you to compute with other people and still retain the same guarantees that you get from SNARKs. To put this a bit more concrete, so what I'm talking about or what problems collaborative SNARKs can solve today is like, we have a very immediate problem, like it is this first one that we're seeing now a lot of client-side CK applications that care about privacy, or where the use case is inherently, or the data, the witness used in these use cases is inherently sensitive. And as today, we have some problems with client-side proof generation. It just, for some complex proofs, it is too slow. The UX is good, or even maybe the memory requirement that you have exceed what any phone can do, or at least what the most users have. And so for this use case, it would be nice to have a secure way to outsource your proof generation. This is kind of a very generic problem from outsourced computation, but even if this is solved, there's this more fundamental problem or fundamental limitation of CK that this doesn't allow you to collaborate with other parties. So, for example, think about any matching algorithm. A lot of Web2 apps, like dating apps or Uber, are centered around finding a match between different parties. If you're only using ZK, this is not possible. So if you do not introduce other technologies, you would still end up with like a central operator performing this matching, and you wouldn't be better than what we have now. Now, MPC can get you both. So for the first problem, the private proof delegation and the private shared state, which is often this problem called in the blockchain ecosystem. And I want to walk you through how this works with collaborative SNARKs. First, for this private proof generation, this is the, let's say, more intuitive part, and then the private shared state. What's next? So let's assume we want to build something like a ZK proving market, but now MPC enabled, so such that you can also outsource your proof generation, even though the witness, so the underlying data, is sensitive in nature. And what a user would do in this case, the user would just request this computation from a ZK proof market, like these proof markets are working already today. And then there is the selection of some nodes of a decentralized set that will then actually perform the computation. And once these nodes are selected, the user's secret share. So this is a term of the MPC language. This is kind of, you can think of one-time pad encryption, 3 parts of the witness, and sends this to this node. So 3 is just an arbitrary number where I've chosen because it's easier to illustrate than, let's say, 1000. And now the actual SNARK computation, the ZK computation, happens between these 3 nodes. So their whole proof generation process, computing the SNARK, the proof system, everything is wrapped into an MPC protocol, such that the nodes that are computing this do not learn anything about the underlying witness of the computation. And what's very interesting is that the end product, so the proof that comes out of this proof generation, doesn't look any different from a proof generation which you do with traditional SNARKs. So you can use the same verifiers, you don't have to rebuild all that stuff. From there, the whole chain, what you would use for like verification, aggregation, can be the same as with traditional SNARKs. Now, that you want to have some properties of MPC and ZK together is a bit of a no-brainer, but usually we struggle to have even one of these technology be performant enough to work well for use cases. So it was always like, yeah, sure, it would be nice to combine those 2, or with FHE or whatever, but doesn't this blow up in my face with the performance? I've even struggled to get one at the range where it makes sense for my users. And it turned out, this paper in 2022, that it showed that MPC and zero knowledge proofs work really well together. And this is because of the type of nature of operations you do mostly in ZK proofs. In ZK proofs, you mostly do stuff like FFTs, MSMs, and so on. This maybe make around 80% of your computation. And these operations are linear. And the basic rule for MPC is that for linear computations, you do not have to communicate with the other parties. So it is very, very fast, like how even as fast as you would do it natively. What slows you down in an MPC are non-linear operations where you do have communication between these parties, and as ZK proofs tend to be highly linear, this is kind of goes well hand in hand. And one of the main, let's say, quote from this paper is that whatever you can do with a single proof, so in the traditional SNARK setting, you can also do in a collaborative SNARK setting with little to no overhead and latency. Of course, you pay the costs of now maybe having 3 provers instead of 1. So for the cost, the more provers you add, you have this additional costs, but you don't suffer from latency. Now, what have we done in this area? We have done the first general purpose tooling for collaborative SNARKs. Currently it is based on Circum, that's why we call it coCircum. And we could verify these numbers from the paper, like coCircum matches the performance of SNARKs so far. So you see this, these two lines are pretty similar, and the green line down, this is rapid SNARKs. And as in the paper, there is no reason why you cannot go to this rapid SNARKs or very close to it with a bit more engineering and optimizing. So this is very confident, and we're talking to several protocols here that rely on client-side proving, but the proof generation takes too long, that want to outsource this into such an MPC setting. Before we go on and talking about the private shared state, so the use case where you have multiple parties inputting private data into a proof, I want to just make some pause to maybe have some questions, if there are any for this use case so far. Okay, then maybe later, or let's go on with the proof generation is now done. We know how to make a proof in a collaborative fashion. And the even more interesting, at least for medium-term and long-term use case, is because it goes beyond the capabilities of what ZK does. It's not just a banded solution because client-side proving isn't fast enough, but opens up new applications and design spaces. Is, again, one RCK proofs not enough. And it's like, I just touched up briefly on this on marketplaces, so wherever you have some sort of a matching algorithm, you can think of it like in the private state, which we have on ADIO, for example, AdStack, or the CK-based smart contract networks. Everybody has a private state, but cannot really collaborate with another person on this private state unless you open it or transfer ownership to this person. And as we're concerned, you want to retain your data ownership without having the ability to compute on it, because otherwise the data is not as valuable and useful to you. Where you see similar patterns is like in games. So for example, poker, if you want to play on-chain poker, you have some states you want to hide from your opponents, and but still you have to compute the game logic and the verifiability in some form, for example a CK proof, and then you can use collaborative SNARKs to solve this problem. Another example that often comes up is like any type of game where you have a fog of war that is very likely to benefit from collaborative SNARKs. And to show this, we have created our own demonstration, which we did during EFCC this year, which we called the Max Big Challenge. This was a very simple guessing game. So suppose we put 1K into a smart contract, and user had to guess a number between 1 and 1,000. And how would we decide on a winner? The winner would be the person that has the highest unique guess. So being greedy and going for 999 wasn't really the best option. But also going for 1 was also not good, because you would get the money that you have guessed. So if you go for 1 and be sure you bring the lowest and the only single one, you just would get $1. Now, why do you need something with infrastructure that isn't there out yet for this demonstration? So let's think about this, for example, in the public state. If you would do this on-chain with a public state, you would see every guess. And so you could easily game this demonstration and this challenge by just looking at the end, what are the guesses and how should I guess such that I win. Second, let's do it private. Then at least you get rid of this somebody swooping in at the last time and getting the prize. But once the game ends and everybody has the guess in its own private state, who should determine the winner? So who does open these private states, shuffle them, and see which is the highest unique bit? This would be a centralized layer. So I think you see this limitation, and that's where coSNARKs play handy. They can offer these capabilities without introducing a new centralized operator, but doing this on a protocol level with cryptography. So end-to-end flow of this guessing game was like you had an UI, the user connects the wallet, submits a guess, signs it, and secret shares all this, the guess, and so secret shares the guess to the network directly from the client. So this is what we have seen also before from the private proof market. Then there goes some stuff on that makes just like process the guess, validate and store the guesses. And the interesting stuff is now to determine the winner of the computation. So the guesses are sent to the MPC network. They have the secret shares of, let's say, 1,000 users. And now they perform the computation. And the computation in this case is like sorting all of these guesses and getting rid of double values. And then the single highest that is still available wins the prize. And you do this all in an MPC setting, so you compute over the secret shares, never open the secret shares. And in the end, the protocol produces a SNARK that can go then on chain and be verified, and you can automatically pay out the prize to a winner. Yeah, the winning guess was quite high. It was like 923. I think this was really the unique highest guess. What you learn from this is that the proof generation is extremely fast. This took just a few seconds. Computing the final winner in MPC is a bit more tricky. So this is where most of the computation time took place. But this was with a highly unoptimized code just for feasibility. So if you want to look how far can we go with MPC and this collaborative SNARKs, we have a proof of concept that is based just on MPC, and where we see how big of applications can really do with MPC. And this is from a work with WorldCoin, where we MPC-fied their uniqueness service check. So this is the part of the WorldCoin tech tree where once you go to an orb and want to verify, the iris code gets uploaded to a database, and it will be checked if you're already in this database. So this is kind of a Hamming distance check to see if you're very close to one of the iris code that is in the database, because if you are, this would indicate that you already registered. And so from the centralized database, we made a protocol that secret shares every iris code. So there is no central database as of now in the WorldCoin protocol for this uniqueness check. This is distributed among servers, and the challenge now is, once you want to compute if a new person is already in the system, you cannot just check it because they're only secret shares. These are just random values for each of the participating parties. So you have to do an MPC protocol, a computation in MPC to check if this new person is already in the system. And the system is huge, so the system has 6 million users, and that's where the bottleneck is. So you have to do an MPC computation over a database with 6 million users. And once we started in our end of last year, the best academic work was like they could do one uniqueness check per day. And this is kind of doesn't make sense for the project. You cannot scale on if you onboard one user per day, at least not for this project. And we did a lot of optimizing, combining different MPC protocols in new ways, and also getting to the GPUs, so moving from CPUs to GPUs to make it now to like 10 uniqueness checks per second. This is kind of the benchmark or the lower bound where the system works very smoothly. And to see this is like an improvement of 5 orders of magnitude. And I just want to show you this, like what is still possible in MPC, even if you don't like optimize for asymptotics, but just for the concrete numbers, doing a lot of engineering, combining it in a clever way. So there's still a lot of room of improvement for MPC, and this directly translates then also the coSNARK setting that we're most interested in. yeah, and how this works in this, just as a brief overview, is like you have the orb here, the user that gets the signed image, and this signed image then is turned into iris codes, and those iris codes are secreted directly from the users to the MPC parties, and the result is again back with the user if he can go on or not to verify to get this wall ID. Now the overall goal or the vision of TACEO is to, like TLS secured the communication, this worked pretty well, but we have now this gap that computation is not secured in the internet. So how we secure it today is like we just trust the centralized operator, but we think we can do a lot of better here, especially with cryptography like ZK, FHE, and MPC. And we depart this mission by combining MPC and ZK. And currently, as I've shown you, we have done this for Circum, which is, let's say, on the developer experience far to the left. And maybe if you have on the far right, like something like Rust, we want to move this needle from left to right, going over some ZK DSLs. For example, we're currently looking into NOR to make collaborative SNARKs accessible for more developers. And yeah, with the end goal to be as developer friendly as possible, while not losing out on performance, but even gaining performance through what the works we have seen for protocols on the MPC protocol level. Yeah, happy to take any questions.
Maybe clarifying, so the way in which a coSNARK differs from like a SNARK is that you first have this witness generation where things happen a little bit different that maybe you didn't go fully into, and then you have your normal proof generation. Is this correct?
So I would say there's two different use cases. So the first use case, you just do the proof generation in a different way. So the private proof delegation, the proof generation is done in a different way, in an MPC-fied way. And the witness generation stays the same. But if you have input from multiple parties, you also do the witness generation in an MPC protocol.
That was the shared...
private shared state, exactly. So witness generation MPC is only needed if you have really input from multiple parties. If you only care about outsourcing my proof, if I only care about outsourcing my proof, I can do the witness generation, for example, locally, because it's not as complex as the computation itself, and then just do the proof generation in an MPC-fied way. But the proof generation always is in an MPC protocol. So always differs. For example, for coCircum, we had to implement Grove 16 and Blanc in an MPC protocol. So this is a completely different proofing backends.
And this is where you mentioned like the access pattern. You have to like pay attention to certain little subtle things differently.
Oh, can you expand on this?
So like in the circuit, if you have branching on ifs or loops or anything like that, and it's MPC, you have to not reveal the access pattern there?
Exactly. So in MPC, you kind of, a mental model is you have to do both branches just to not leak which branch you did go, because this would tell something about the underlying data. Yeah.
Did you say that you got a lot of time improvements with the MPC approach?
So to be clarified, so the improvements were on the WorldCoin use case. This uses MPC only, so from the state-of-the-art MPC academic papers to the actual implementation. What you don't get out of collaborative SNARKs is faster SNARKs.
Okay.
So this is not possible, except maybe in the setting where you say, okay, client-side the proof takes me 10 seconds, then if outsourcing with collaborative SNARKs, this can get you to maybe 1 second. This is possible, but not on the same device with the same hardware setting. You always introduce some overhead here.
What does that outsourcing look like? And like where would it go? Would it go to like a prover network or?
Exactly. So you can imagine one thing I imagine is like you could also use free proof of networks, where each of the MPC proofers is located in one of those proof of networks.
Okay, 3 separate proof networks.
For example, yeah.
And it still privacy preserving because of the MPC.
Exactly. You have an MPC, you have an inherent non-collusion assumption, so you trust that, for example, proof of network A, B, and C do not collude and share data with each other. But as long as they uphold to this non-collusion principle, then it's secure and private.
Any other questions? Thank you so much.
Thank you.